Hey everybody, welcome back to part 2 of gas stoichiometry. So I realized after I did yesterday's lesson, I think that was the first one where I had the camera on the whole time. And I was looking at the video lesson as it was uploading and realizing I wasn't really looking at the camera. So I wasn't really looking at you guys. I was staring at my notes off to the side. So I'm going to try and do a better job of maintaining eye contact with my audience, you guys, as I work through these problems. But we'll see how that goes. So today we're doing gas stoich part 2, and really the only difference to what's going on today is we're going to be using the ideal gas constant, R. So hopefully you remember R is 8.314 kilopascal liter over mole Kelvin. And you don't have to have that memorized. It's on your data sheet at the back, so you can refer to it. And the important thing is that you get the units correct. The kilopascal liters is on top with the numerical value of 8.314, and the moles Kelvin is on the bottom, and this is a ratio, so we can flip it, just like we can take molar mass and write it as grams per mole or moles per gram, and we can take molar volume, 24.8 liters per mole, and we can flip it and write it as moles over 24.8 liters. We can flip this one as well. So if we flip it, it'll be mole Kelvin on top, 8.314 kilopascal liter on the bottom. So it's a ratio, it's flippable, and we do that when we need to cancel out units. So if we were looking for a volume of gas at R, we would leave it in this form because we'd be looking for the liters, and we want liters on top. So just remember that as we go through these problems, and I'll review it with you as well. So the plan is we're going to do 4 problems, take maybe 20 minutes, and then you guys will have some time to work on practicing those. And the final assignment for gas stoich is just a little 2-day unit, and then we're moving on to solution stoichiometry. Hopefully you're a Harry Potter fan, because just for fun, we're going to put a bit of a Harry Potter spin on it, and you'll be sorted into your houses. So you're going to need to take the online Google survey so that I know which house you identify with: Slytherin, Hufflepuff, Ravenclaw, or Gryffindor. Okay, let's rock and roll. So first question. How could you determine the volume of oxygen at 20 degrees Celsius and 97 kilopascals produced when 5 grams of mercury 2 oxide is decomposed? Okay, how do we know this is a stoich problem? How do we know we need a balanced chemical equation? Because we have a chemical reaction. Mercury 2 oxide is decomposing. So mercury 2 oxide, Hg2 plus, O2 minus, makes HgO. So that's a 2 plus and a 2 minus, balance out. It's an ionic compound, so it's solid. It decomposes. Decomposing usually means into its elements. Elements would be mercury and oxygen, written as O2. Oxygen is a gas. Mercury is a liquid from the periodic table. So now we need to balance it. So I've got 1 mercury, 2 oxygen on the right, 1 on the left. So I need to put a 2 in front of that, which means a 2 in front of that. And now we have a balanced chemical equation. Yay. Okay. What are we doing here? So we are looking for the volume of oxygen. So I'm just going to write volume of oxygen gas. Okay, and remember, in a stoich problem, when you're trying to convert from one chemical to another, we need to know the moles or the amounts. We can get the moles of mercury 2 oxide from its mass. So mass times molar mass. 5 grams of mercury 2 oxide times its molar mass, which is 1 mole over 216.59 grams. Okay, so now I have the moles of mercury 2 oxide, but I'm interested in the volume of oxygen. So I need to turn mercury oxide into oxygen. 2 moles turns into 1. So I'm looking for oxygen. 1 mole of oxygen on top, the chemical we're looking for. We're going to cancel out the mercury oxide by putting its coefficient, 2 moles of mercury oxide on the bottom. Okay, let's do some canceling here. Grams cancel out. The moles of HGO cancel out. So right now I have solved for moles of oxygen, and I'm looking for the volume of oxygen under these conditions. So because it's giving me a temperature and a pressure, that's telling me that I need to use R. It's not saying STP or SATP. If it was, I could use those shortcuts, right? 22.4 or 24.8 liters per mole. But it's not STP and it's not SATP. Those are out. It's giving me a specific temperature and pressure, so I need to use R. So now the question is, how do I put R in here? What goes on top and what goes on the bottom? Well, we're looking for volume of oxygen, so I want liters on top. And I'm trying to cancel out moles, so I want moles on the bottom. So 8.314. I want to put the kilopascal liters on top because I'm interested in keeping liters. And the mole Kelvin goes on the bottom. So we're using this form. Kilopascal liter on top, moles Kelvin on the bottom. Kilopascal liter on top, mole Kelvin on the bottom. Okay, so what cancels out now? Let's see. Moles cancels out. I want liters of oxygen. Okay, there's what I want. So I need to get rid of kPa and Kelvin. Those are my last two steps. kPa is right here, 96 kilopascals. Put it on the bottom so that it cancels out with the kilopascals on the top. I need to get rid of Kelvin. It's on the bottom, so Kelvin needs to go on the top. And there it is, 20 degrees Celsius. Add 273, and that becomes 293 Kelvin. Okay, 293 Kelvin. All right, Kelvin is gone. There we go. There's nothing left in here except the unit of liters and the chemical formula of oxygen. So I get liters of O2, which is what we're looking for, volume of oxygen. Plug everything into your calculator, and you should get 0.2928 liters. And then we go through and check our sig digs. 3, 5, 4, 3, 3. So my final answer is 3, and the 8 will round the 2 up to 3, 0.293 liters of oxygen. Whoa, what the heck? That was going to be a happy face. It turned into some type of abomination. Let's try that again. There we go. Okay, awesome. So 1 down, 3 to go. Hopefully you're with me. They all follow the same pattern. So once you get one of them, you're good to go. Okay. If you're feeling super confident, you can try this one on your own. If you'd like to see one more example, then you can follow along with me in your notes. Okay, this one is affectionately titled Example Number 2. Lovely. Okay, how many grams of water vapor are produced if 20 liters of propane is burned at that temperature and that pressure? So that's 293 Kelvin, 1000 kilopascal. Okay, so it looks like we're going to need R. Just going to put that off to the side. I know I need R, kilopascal liter. I know I need R because I have a temperature and a pressure, and they are not STP or SATP. So that's where R comes into play. That's for all gases that aren't at STP or SATP. Okay, so we're given propane and we're looking for water. So it's a chemical reaction. It's combustion of propane. We did this one yesterday. C3H8 burns, reacts with oxygen to produce 3 CO2s, 4 H2Os, and those are both gases. Gas. Balance at 3 and 3, so that is 4 and 6 is 10, 5, 10 oxygen. Okay, so there's our balanced equation for combustion of propane. How many grams of water vapor, mass of H2O vapor or gas? Stoichiometry, we got to start with the moles, and we can get it from 20 liters of propane at that temperature and pressure. So here is the temperature, pressure, and volume. That's how we'll get our moles. I can cancel those three out and get moles. So I'm looking for moles, so I'm going to flip this thing. Moles, Kelvin on top, 8.314 kilopascal liters on the bottom. That's going to allow me to get my moles. How do I do that? I'm going to cancel out the other three because they're all given. Liters. 20 liters of propane. Okay. Liters cancels out. Kelvin needs to go on the bottom. 293 Kelvin. Okay. Kelvins cancel out. Kilopascals on the bottom. I need it on the top. And it is 1000 kPa. Okay. Kilopascals cancel out. So I used R to turn a volume of propane into moles of propane, C3H8. Everything else is canceled out. Kelvin, kilopascal, liter. So using that temperature, that pressure, and that volume, and R, we were able to get the moles of propane. Now the question is asking us for the mass of water. So we have to turn propane into water. We'll use our molar ratio, and we're looking for water. So 4 moles of water for every 1 mole of propane. Okay, if I quit right now, what have I solved for? Propanes cancel out. It looks like we have moles of water, and we want the mass of water. So my last step would be to times it by the molar mass of water. And water's molar mass is 18.02 grams per mole. Holy smokes. Okay, moles cancel out, and I am left with grams of water. So the units tell me I have it right. Grams of H2O. Multiply everything on the top by everything on the bottom, and you should get 591.78 grams of H2O. Sig digs, we got 4, 3, 3, 4, and 4. So our final answer is 3. 592 grams of H2O. Got it? Whew. Okay, so you can see there's lots of canceling of units in here. This is really just dimensional analysis, paying attention to units and making sure they all cancel out, and having a balanced chemical equation. Okay, so we're going to move on to number 3 now. Affectionately, it doesn't have a title. Okay, so question number 3. 1,000 grams of carbon dioxide is we're using the same balanced equation. Okay, so it's propane. So I'm just going to bring that balanced equation down here. C3H8 502. C3, oh my gosh, what a mess. C3H8 plus 502 makes 3 CO2s and 4 waters. Okay, there's our balanced equation. Good. Okay. Let's put that up there. All right, if 1,000 grams of carbon dioxide is produced, how many liters of propane? Okay, we're looking for volume of propane. Liters of propane, and we have mass of carbon. So in every Stoich problem, there's always a way to get the moles of a chemical. So we're going to do it from the mass of carbon dioxide. We can get the moles. 1,000 grams of CO2 times its molar mass will give us the moles of CO2. So that's 44. Whoops, I wrote it upside down. It's going to be moles on top. 44.01 grams on the bottom. Mass times molar mass, the grams will cancel out, and I will get the moles of CO2. Okay, good. We have moles of CO2, but we're interested in volume of propane. So we got to turn CO2 into propane. We put what we're looking for on top. 1 propane reacts for every 3 CO2 produced. CO2s cancel out, and now we have moles of propane. Okay, moles of propane, and we want volume. So we've got a gas, moles of propane. We need it in its gas conditions. There's our temperature, 283 Kelvin. There's our pressure. So we can use R to cancel all of this stuff out. Just going to put that down to the bottom here. There's our answer, 22.3 liters. Hopefully that works for us. Okay. So R, which way do I write R? What am I looking for on top? What am I looking for on the bottom? I've got moles on top and I need to cancel it out. So moles Kelvin on the bottom. I'm looking for liters. So 8.314 kilopascal liters on the top. Let's see if that works for us. So the moles cancel out. I'm looking for liters of propane. So there it is. I keep propane, I keep liters. I need to cancel out the kilopascal, cancel out the Kelvin. All right, so how do I do that? Okay, what goes on top, what goes on the bottom in order to make that cancel out? Okay, so kilopascal, there it is on top. So I put this one on the bottom. 800 kilopascal on the bottom. Gonzo. Okay, Kelvin on the bottom. I need Kelvin on the top. There it is, 283 Kelvin. Kelvin cancels out. You can see how I'm really paying attention to units and making sure that they all cancel out. You got to pay attention to those little details. Okay, what's left? Everything's canceled out except this liters and this propane. So when I get my final answer, it's going to represent liters of propane. And that's good because that's what we're looking for, volume of propane. So everything on the top multiplied, divided by everything on the bottom, and we get 22.276 liters. Sig digs 3, 3, 4, 4, 4, 3 sig digs, 22.3 liters of propane. Cool. 3 down, 1 to go. How's everybody doing? 2 thumbs up. 1 up, 1 down. Hopefully not 2 down. Okay. All right, last one. And you're good to go on gas Stoich. Okay, if you're feeling really confident, you can pause the video right now, try this one on your own, and see how you do. That's probably a good idea. And if not, then you can watch as I go through this one. All right, so we've got solid zinc with nitric acid. Zinc, solid, reacting with nitric acid to produce hydrogen gas and zinc nitrate. Ionic compound, high solubility, aqueous. Okay, balanced. 2 nitrates, 2 nitrates. Nitrates are balanced, 2 hydrogen, 1 zinc, 1 zinc. Hey, we're balanced. Okay, that was pretty easy. All right, so what's the pattern to solve this one? So we have a mass of zinc, so that's our starting point. If we have the mass, we can turn that into moles using molar mass. And we're looking for volume of hydrogen gas. Volume of hydrogen gas. Okay, mass times molar mass to get us started. 4 grams of zinc Molar mass of zinc is 65.41 grams per mole. I need to flip it and put the moles on top. 65.41 grams on the bottom. Cancel those out and we get moles of zinc. Okay, we have moles of zinc, and we know that 1 mole of zinc makes 1 mole of hydrogen gas. Okay, so there's our molar ratio. We're looking for the hydrogen gas. 1 hydrogen gas for every 1 zinc using our molar ratio. So now I can cancel the zincs out, and we have solved for moles of hydrogen. We're just looking at unit analysis, moles of hydrogen. Okay, so we want the volume of hydrogen at that pressure and 273, 283, 294 Kelvin, that temperature. All right, so I want you guys to think about this carefully. We're going to need R because we have a temperature and a pressure. How am I going to write R so that units cancel out? And we're looking for volume of hydrogen. Okay, so what's the strategy for doing that? Okay, so we want liters on top because we're looking for volume, and we want to cancel out the moles. So put the moles on the bottom. 8.314 kilopascal liter over mole Kelvin. Okay, so moles are gone. So now I no longer have moles of hydrogen. I'm looking for the volume of hydrogen. So there it is. There's my liters. There's my hydrogen. I just have to get rid of the kilopascals and the Kelvin. Kilopascals is on the top, so we'll put it on the bottom. 98 kilopascals. And then we've got Kelvin on the bottom, so I put Kelvin on the top. And we can cancel out the Kelvins. Cancel out the kilopascals, and we are left with liters of hydrogen. Plug everything in, and you get 1.525 liters. And this one is 2 sig digs, so 1.5 liters. The number that's in here is wrong. Okay, 2 sig digs because of this guy. Well, and this one, they're both 2 sig digs. 1.5 liters. Okay, so hopefully you've been paying careful attention and you've got this figured out. And you could also tell me how many times did I change the position of the hat that I'm wearing on my head. If you go back to the start of the video, you'll notice that I wasn't even wearing a hat. I tried to sneak it in the middle of the video, and then I moved it around a couple times. So how many times? Make your guess. I got to figure the answer too. Okay, so including the one that I just did, that was a total of 5 flips. If you don't believe me, go back and fast forward through the video and you'll see 5 flips. So hopefully you're paying attention and you caught that too. Keep you guys sharp and awake out there. Okay, so your assignment, you've got these questions that you can work on. I will give you solutions to those. And then once you have them done and you're feeling confident, oh my gosh, that is messy. What is going on? Once you're feeling confident, then you can try the wrap up assignment and the Stoich quiz. All right. Everybody take care. Have a great day. Enjoy this awesome weather that we're having. So nice to finally have spring here. And I'll see you guys tomorrow.